it increase its yield strength. Right? So if you put more, right, it's good news. Okay? So over here, we have 0.269, right? And with 0.269, you have high yield strength, and this is contributed due to what? Silicon. No doubt your carbon is low, right? Because of the addition of silicon, right? Your A values get high if it's in what? Martensite phase. Okay? And this is how you can more or less have a good guess. Okay? You can have a good guess, okay, what is going on? Why do they put this? They put this because they want the what? The high what? Yield strength. As I say, this is from any textbooks, okay, or any information you can get from textbook, material science textbooks. Okay, it's always there. And then you have D.
Eugene?
Yes.
So just to confirm, for the AISI 1045, there's no silicon content in it, right? Okay.
No. Okay. So B is your boron. Okay. And if you see any material that has boron, you have to be careful. Okay. This is one deadly alloy to have. Okay. So it's between 0.001% B and go up to 0.003%, right? What it does is increases, right, strain hardening, sensitivity. Okay? It increases strain hardening sensitivity. So over here, you realize, now remember I told you guys, right, you cannot decouple BNN. These two values, right, is due to what? The addition of boron. Could you imagine if we are without these numbers, let's say we don't know A, B, and N at all, and we have this chemical composition in mind, we can more or less guess, right, that this material is going to have very high what? Yield strength, and is very sensitive to strain hardening because of what? Boron. Even before carrying out any tensile test. Even before you carry out any tensile test, by looking at the chemical composition, by looking at the microstructure, the final microstructure during application, right? We can have a very intelligent guess how our mechanical behavior prediction, a good guess, okay, a good guess what's going on. Now, then the next thing that I want to highlight, okay, I will get rid of this piece down here. This is so exciting, you know. I need some drugs to calm me down when I teach this, I think. Okay. Then the next thing we're going to look at is manganese. Okay, which is Mn. Okay, so manganese, when it's less than 1%, okay, it will prevent material from brittle failure. Okay, from brittle failure. And then if manganese, so usually they'll come up with a range, as you can see. So the textbook did write when manganese is between, or not between. If manganese is greater than 1%, what does it do? It increases hardened ability, right? Increases hardened ability by lowering the phase transformation temperature. Okay, so as you can see, for our manganese, for Uzbor, it's at 1.2. Where for AISI 10.5 is between 0.6 to 0.9. So why, the question now is, why is this important? Right? Why is this important? So I'm going to sketch for you why this is critical. Okay. So by now you all should have these numbers now. Okay. I'm going to erase and I'll tell you why it's important. So what the greater than 1% means, and what do we mean by increasing hardenability? Right. So as engineer, we know by looking at the equation, the plastic flow stress equation. Right. So this is what? Strain hardening. Right. But what do they mean by hardenability? How can they increase the or make it easier? Increase hardenability means what? Means make workpiece or make material hardening easier. When we say easier, it can be based on what? Energy consumption. Okay. So what I'm going to do now is we're going to take a break. Okay. We're going to take a break, and then we come back at 8:50. Okay. We're going to take a break, and we come back at 8:50.